Thank you very much. I'm very happy to be here in person. It's now close to the coffee break, so I'll try to talk as quickly as possible. I switched this talk with Viktor Doroshenko, who unfortunately had to leave because he had to pick somebody up. I thought this talk would have been earlier in the session, and therefore I plan to do this a bit more as an introductory talk. So some of the things that you've seen now in the previous talks will be contained in here, but I think there will be slightly different aspects here. So I'd like to talk about magnetic accretion in neutron star X-ray binaries, summary of a few things that I've been doing with quite a few people, and I have to especially thank Ekaterina Sokolova-Lapa, who's my PhD student, but essentially has the qualification of a fifth-year postdoc, and she does much nicer graphics than I do. So I'm stealing a few things from her. So we're talking in this talk mainly about high-mass X-ray binaries here that have fairly strong magnetic fields. So we're talking about high B field sources, not about CVs or the wimpy 10 to the 6 Gauss objects or 10 to the 7 Gauss objects that we heard so far. And I'll be talking a bit about accretion processes in these systems, essentially going from higher luminosities down to lower luminosities. Because this is only a 15-minute talk, I decided not to talk about cyclotron lines because there will probably be some other talks that cover that field. So where do we stand in terms of accretion? We had in the first talk in this session already a presentation about torquing of neutron stars, and we see that the interaction between the accretion flow, which comes from the companion star, and the neutron star strongly depends on the mass accretion rate. And I think we also saw in the discussion between Sergey that there are some issues about the nomenclature of these systems that are always confusing, right? We often talk really about neutron stars in quiescence when they are not in quiescence because we see them, so they are not quiescent. And there is, I think, a bit of disconnect sometimes between theorists and the observers about these things, and we should use some coffee break here to agree a bit among these different phases. So if you are far away, you can't accrete because you're outside of the light cylinder, and then as the mass accretion rate changes, the behavior of the system really depends on where are you stopping on the where the material is being stopped. So you have a stopping radius there, you have a co-rotation radius there, and you have a gravitational radius there, and depending on where these radii are, different physics happens. And the boundaries between these different phases that I'm showing here are not that well defined as people often might need. That's why we need, for example, observations similar to the ones that Victor also used, because a lot of these transitions between individual regimes that we're seeing, both here in a case where we're not yet accreting, but also we'll see that later when accretion happens, are extremely badly defined. It's mainly all going back to 1970s work because that's something you can do analytically, and unfortunately there is not a full model for accretion and the accretion column available yet. And I would like to have everybody keep that in mind when you look at the output of these observations, because there's a strong observational and theoretical bias in that just because we're using approximations that are too simple, in my opinion. The good thing is they all give useful information back, but especially for the theorists, I would like to urge you not to take hard numbers that we derive from the observations too seriously just because we are using a too simple model. On the other hand, theorists, this is your opportunity to do a bit more about modeling accretion columns and modeling accretion onto these systems than before, because as I'll show you, these systems are very useful to get something out on the magnetic field geometry. So having said this, when accretion starts, what's going on? Essentially, as a function of the mass accretion rate, we can see these different regimes that were also previously mentioned. And in the brightest sources, essentially, we think that from the accreting neutron stars, once they are really in outburst, we have a phase where we are effectively observing emission from a radiative shock. So we have a very small region. The spot on the neutron star is a square kilometer. It's often much less than that, to the point that if you draw to scale images of neutron stars with accretion spots, you don't see them, which is very confusing if you do that the first time and you've developed the code for a long time, and then you plot the image and you don't see anything, and you think, like, what's going on? And then you realize what a few hundred meters really means, even on a 10-kilometer neutron star. So we have small structures in there, and the luminosity that's released there is so strong that we are super Eddington. So you get essentially the material that falls onto the neutron star is being stopped by the radiation that tries to come out. That's the most complex situation there, but that's also the situation where we have most of the observations. There are only very few models available, which you could all criticize by a lot. The Becker and Wolf model, because it's very much an analytical model, to the point that the approximations in there make a few of the outcomes questionable. Other models, however, suffer from the same problem. But in general, we all agree that the overall spectrum that we observe, and this is here Hercules X1, for example, it consists of a power law, some turnover, and then a cyclotron line. So the interaction between the radiation and quantized electrons in the accretion column is a combination of Bremsstrahlung, cyclotron emission, and some black body radiation. And these different components, as they vary, determine what the spectral shape looks like. One should say that the problem is, unfortunately, that these models, well, that the observations essentially tell us that these systems have spectra that look almost like an exponentially cut off power law spectrum. And so essentially all physical models that give you something that is as boring as an exponentially cut off power law essentially explain the data. So the interpretation of individual components that we see in here is difficult. This will change. It has already been changed with the launch of IXPE. And with IXPE, for example, we are seeing that, Viktor Doroshenko has shown that, for example, we're seeing that the polarization that we see in the X-rays is very different from that has been observed, that has been predicted. The modeling also often, especially when done by theorists, is done in flux space, which you should not do when you work with X-rays. The Becker and Wolf model, to my knowledge, together with one by Farinelli, is the only one where you can do direct modeling of data, which is crucial if you really want to constrain the model. And I refer you to this paper by Philipp Thalhammer from my group about the techniques that have to be used to do that. The summary is it's extremely painful. A second thing that you can do to get information on the accretion column is by looking at the pulsations, and we've also seen examples there already. This is an outburst of EXO 2030, a very famous source that has been observed quite often, and we were very lucky about 2 years ago to see a bright outburst of this source. It's one of these bright outbursts that tend to happen over Christmas, because that's when sources decide to be interesting. And what you can already see here from these observations is that the pulse profile is changing over this observation. And that gives you some indications that the accretion column must change. It's a bit difficult to see here, but if you do a map like this, where you plot each pulse profile from these 50 observations as a function of the count rate, independent of whether it's into the outburst or after the outburst, because there's no hysteresis in the system, you see this picture emerge. So you have the main peak here, yellow is bright. There's always a dark dip here, probably because we are looking through the accretion stream, but you see that these different components here are changing in strength as the luminosity changes. So this means that the emission characteristics that we are seeing from the column are dramatically changing. And that has to do with these critical luminosities and the switch between the different stages in the accretion column that Victor also mentioned before. We can try to deconvolve these pulse profiles by modeling the emission of the accretion column essentially as a fan beam and a pencil beam. So you take some Gaussians, put the Gaussians out to the side of a column and put the Gaussians onto the top of the column, and then you put them into a relativistic light bending code and you generate synthetic pulse profiles, and then you compare those with the observations. And what you find, and I'm not sure whether you, yes, you can see this better than I can see this here on the screen, is you have an emission characteristics that consists essentially of these two beams, which slightly change with luminosity. And the strong change that we see in the pulse profile is a change here from these contributions. What's more interesting here is that if you look at the location of the emitters, which is the second thing that you can play with, so the hotspots on the surface of the neutron star, it looks very much not like a dipole. This is something that we're now seeing more and more in multiple neutron star systems. It appears as if pretty much none of the neutron stars look like the ones that we draw in our sketches. The dipole, I think, is about to die in the next few years. You might have read about the neutron star configurations that were measured in low B field systems with NICER, and they have the same problem, right? They have two spots on the same hemisphere in a very complex situation. So that has strong implications, I think, for the interpretation of the data. So now if you go to lower luminosities, the column will be smaller and smaller, and we are in a very nice situation then, namely one in which the geometry of the column does not matter, which is good because we switch off a lot of the physics that we don't understand. And Sergei here, for example, who really was one of the first people to deeply look into this, what some people call the quiescent state, but there are photons, so it's not. The low luminosity state, you realize that there is a double hump structure in essentially all of the observations that we have at this state. This is only possible because now we have hard instruments like NuSTAR deadline next week, right? That are able to go out to 50 kV. So the question is, how do you interpret these observations? We've developed together with colleagues in Moscow, Konstantin Postnov and his students, a model where we do radiative transfer through one of these settling structures here, where you have a very small structure that where we can propagate the radiation through, and the resulting spectra show that you can interpret the double hump as a thermal hump and then as a second hump that has a substructure because of the strong magnetic field. So the dip in the middle in this model is interpreted as a cyclotron resonant feature. There are other models that can explain the spectrum as well. We're done, I think, a very decent job to really fit this with the data. And again, and this is a direct fit. And again, also in this case, we have also worked on the phase resolved spectroscopy. Mainly Jakob Stierhoff and Katarina Sokolova-Lapa did that. And if you look at the position of the phase resolved spectra, which suck, to be honest, but we can also model the pulse profiles. We find again, even though we're photon starved, that the poles are not antipodal, but somewhere randomly apparently on the surface of the neutron star. So this is here yet another example that the magnetic field must have higher orders and is not a simple dipole field. So to conclude, we can probe the strong B field. Low luminosity is really cool. I didn't talk about cyclotron lines. I'm looking forward to the questions.